So let me start by congratulating Louis with this festive occasion. We've known each other for many, many years, more than most people here. We met, in fact, in 1981. You probably don't even remember.
It was on before. Okay.
It was on, but it's not very loud. So, should I congratulate Louis again? Okay, congratulations. I was just explaining how long ago it was that we met. It was in 81. It was in Lisbon. It was in Lisbon. Okay, and then after that we met at CERN, and I met him many times here in Madrid. And despite having overlapped with him for so long and having had many enjoyable and very instructive conversations, I managed to write only 2 papers with Louis and with Angel. And I think for 30 years that's a little bit, it should be higher on this top scorers list of yours. But okay, maybe in the next 30 years we can work on that. So this morning, by coincidence, I got an email about the 90th anniversary of Freeman Dyson. So by that standard, you're only halfway your career. We're really all just kids, and we're just starting. And talking about kids, the first speaker is Hans-Peter Nilles, and he's going to talk about the zip code of the standard model of the MSSM particles.
Does it work? Yeah. Okay, so it's a pleasure to be here. Thank you very much for inviting me. It's not just that I can give the talk here, but it means also that I had the privilege to collaborate with Louis some time ago. We had, according to Anna Maria's counting, I have 10 to the 10 reasons to thank him. And it was a great time. We were young, and we were believing that standard model physics was just behind the corner. Now, the first statement, I think, is no longer true, although you say the opposite. And the second one, I don't know what your opinion is about this one. Any case, so today I will talk about some recent work I was doing in constructing string models, and the title is The Zip Code of the MSSM Particles. So Rocky Kolb said your zip has several meanings in the American language. It means the zip code, as I mean it, but zip means also nothing, you see, in that sense. And he said he came somewhat late, so I should not say anything important in the first half hour of my talk, which is probably not so difficult in any case. So the zip code will mean that where do the MSSM fields live in extra dimensions? You see, this could be important. The localization properties of quarks, leptons, and Higgs bosons can have a lot to do with Yukawa couplings. For example, if a particle is confined to be here, and the Higgs boson lives at the train station, then you know this cannot be a large Yukawa coupling. It must be something which is light. So this is one thing, and in fact, what I will try to convey you, that it might very well be good to have the Higgs bosons and the top quark living in the bulk, meaning in the full 10-dimensional string theory, in the full 10-dimensional space of string theory, and that the first 2 families are localized and maybe exhibiting family symmetries, and that will be a quite useful thing to look at it. So the idea is to construct string models which look realistic and then actually look back and find the reason why they are actually realistic, because we have learned by now that we can construct many models which are not realistic. So it's not clear from first principles that string theory gives you the right answer. The legacy from higher dimensions and this localization will also have to do something with supersymmetry breakdown, which I'll come to the second part of my talk. So first I'll start putting some guidelines. One thing to remember is that a family of quarks and leptons seems to be in a spinor representation of SO10. So even if this group is not gauged, this is something to remember and might be useful when you do model construction. So if you start with SO10 and you have a spinor representation, that might give you the right track. We also will assume gauge top Yukawa unification. So the top quark is rather heavy, and it looks in string theory that if the gauge couplings are of order of the string coupling, then the top Yukawa coupling should be the same. So that's something which we assume. We also assume that the presence of discrete symmetries, which can solve a lot of problems which we have, and also by being broken slightly, creating hierarchies. So that's the idea we are going. So now you have to ask the question which group we start with, and then of course from the mathematical point of view the group is E8 because there's a maximal group, whereas when you have SON or SUN there is no maximal group, so the selection is not clear. But E8 of course does not allow for chiral fermions, at least in 4 dimensions, and then the question is how does this fit to our picture based on SU5 or SO10. And then of course probably you have seen that already. This is the Dynkin diagram of E8. That's the maximal group, and you can go to smaller groups by chopping off something. So this is E7. This would be E6. E6 would not be so bad because it allows already chiral representations in 4 dimensions. So you could have seen that there were some models based on E6 grand unification when you look. So this is something which is good. Then you chop off 1, so this is E5, so this is the exceptional group 5, which of course is not exceptional. It coincides with D5. So actually you could in that sense understand SO10 descendant from E8. And moreover, E4 will be A4, will be SU5, and if you chop up 1 more, you actually get to SU3 to SU2. So this is very nice. So now you ask the question, where do I get exceptional groups? And in fact, in string theory, there's a natural way of getting it. This is clear in the E8 cross E8 heterotic string, but also in other theories like M or F theory, you could have E8 enhancement at some singularities in the space, and so this would give you a nice starting point. Strings live in higher dimensions. That's good because a chiral spectrum is possible even with E8, and in 4 dimensions that would not be, so E8 has to be broken, and it provides a source for discrete symmetries, other symmetries, and also we can have other symmetries as a combination of E8 cross S over SO10 and also of the Lorentz group in higher dimension, the SO6 group in higher dimensions. So now I want to talk about geography. So many properties of the models depend on the extra dimensions, location of quarks and leptons relative to the Higgs boson. But also, I will talk about the heterotic string here. There's also a localization of the gauge field, although there is an E8 gauge group in the underlying theory. I will explain that in a moment. So there are smaller gauge groups in various places, and the 4-dimensional gauge group is the common subgroup of these ones. So this would be compactification now on a nice Calabi-Yau manifold. This is beautiful but very complicated. Fields could, for example, live at some points there. This is possible in the moduli space of the group, but of course, if you have a generic Calabi-Yau, that will not happen. So in order to simplify that and also make these properties manifest, it has been suggested that one can use an orbifold. So an orbifold is flat everywhere except at some points or fixed tori. And it has the advantage that since it's flat everywhere, you can do calculations using conformal field theory methods. That's very nice. So here we can now, in this picture of the orbifolds with quarks and leptons, they can be localized. So they can either live in the bulk, that is in 10 dimensions. They can live on fixed points, which I could call 3 branes, although they are not the dynamical branes. They are points in extra dimensions, or they could be fixed tori. That is tori in extra dimensions, and of course living in our 4-dimensional world. So these are the possibilities. And now I can come to this localization of the gauge fields. For example, here, this is a specific model. And in this model, at these various fixed points in the bulk, you have a bigger gauge symmetry. But at these various fixed points, you have smaller gauge group. For example, if the electron will live here at this fixed point, it will be in a complete SO10 representation, because here SO10 is the gauge group. So also the up and the down quarks will live here. Whereas, for example, at these other points here, you have SU4 squared or SU6 cross SU2. So the representations do not come in full multiplets. That's, of course, at the origin of solving, for example, the triplet splitting problem. You should not have the Higgs sitting here, because then it would be in a 10-dimensional representation of SO10, and you would, of course, have the triplets and the doublets. So now you might wonder, what is the gauge group which comes out in this model, which was constructed in a set2 cross set2 orbifold, and it is the common subgroup of those, and you can look at it and you will actually see. So these are now the subgroups, the common subgroups of these two, this one. So this would be some Pati-Salam-like group. You also see that here these two SU6 cross SU2, they are aligned in a different way in the E8. And when all the dust settles, as you see from the title, the standard, you have a model with the standard model gauge group. That's the common gauge group which survives. But you see, you have some places in extra dimensions, if fields are localized there, for example here, then you have a full 16-dimensional representation. So in that sense, you have something which can give you simultaneously full representation, but also split representation, depending where fields do live. So we then took this model, and we actually took the Z6 orbifold and cranked through this. And recently we have extended that to models which are in the Z2, Z4 orbifold. There have also been works in other, in the Z2 cross Z2, Z12, and others. So what we put in is we are looking for models which had a large top quark Yukawa coupling. So this was our input, that we wanted to have this Higgs top unification, and this we should give us 175 GeV Higgs. That fits very well. So we are looking at these models. So we are not looking at models where the top quark Yukawa coupling vanishes. We also look for family symmetries for the first two families. So that was the, and then we wanted to try to get three families, one Higgs pair, and all no chiral exotics and all these kinds we wanted to go through. And we found then several models, several hundred models, which satisfy all these properties. We actually then found, so we have these models, and now we can see why are they actually so successful? What is the property which is shared by them? And we actually also found models which had an R parity and which had a particular solution to the mu problem. Well, I can come back. And then we were also looking at the question of gauge-Gino condensation in the hidden sector and how that would work out with the supersymmetry breaking scale. So now let me just look at the sectors. This is the Z2, Z4 orbifold. So we have an untwisted sector. This is the bulk. This is 6 dimensions. So the states which live in the untwisted sector, these are actually the states which you get when you compactify on a torus. Now when you compactify the theory on a torus, you are kept with n equal to 4 supersymmetry in 4 dimensions. So at 3 level, in some way, the untwisted sector fields, they still feel this extended n equal to 4 supersymmetry. It will be broken because other sectors have less supersymmetry, so at n it will be n equal to 1, but at the first level, it will feel it. And you all know probably when you have heard about these no-scale models, this is actually a reflection of that fact. So there's the untwisted sector. Now there are several twisted sectors. So this is so we can have a Z2 twist theta and a Z4 twist omega. So this would be the omega twisted sector. So we will have 4 fixed tori. And then we go to the omega squared sector. We also have fixed tori. Then we have sector which is theta, which is in the first 2 extra dimensions. So these are also fixed tori. There's a torus here in the third complex extra dimension. We then have the theta omega sector, which is interesting because it actually contains fixed points. So this sector has fixed points in extra dimensions, and they are indicated here. So they're actually 4 times 2 times 2 fixed points. And they are, you see, living in 4 dimensions on a point. So they actually are a sector with n equal to 1 supersymmetry. They don't feel any extended supersymmetry, as the untwisted sector felt with n equal to 4. And of course, the fixed tori felt with an n equal to 2 supersymmetry. So now we can ask the question, where do we find the quarks, leptons, and the Higgs bosons in the model of the mini landscape? So given you have a successful model, can you try to figure out what are the properties of the model? So how does the model achieve a large top quark Yukawa coupling? This is the question. So there is a benchmark model. I will not go through that in detail. The first thing, we are looking at the location of the Higgs boson. So first, we look at the Higgs boson. So there are 2 things which we want to do. We want to have the triplets heavy or projected out so that we have doublet-triplet splitting. And then we also want exactly 2 doublets, Higgs doublet, that should remain light. I mean here exactly 2 comes from, if you construct these models, very often you get 20 Higgs pairs. Now once you have 20 Higgs pairs, you should get rid of 19 of them and keep 1. Now, so first of all, you have to find a good reason how to get rid of 19 of them, which is not so difficult at a given point to get. But then, you see, now you have to find the second reason why this mechanism does not work for the last one. Because typically, when you have found such a mechanism, you can make them heavy, all of them, and that's the so-called mu problem. Of course, in the MSSM, the mu problem is in some way, why is mu so small? You start with 2 doublets, but here actually you also have additional doublets which you have to be heavy, keeping this one small. Now we have actually looked at, so we had these models, and experimentally we now found out that 50–60% of them have a very interesting property, and the property is that one of the Higgs pairs we were not able to make heavy. So in these benchmark models which I showed you, we went up to Yukawa couplings of or mu term of order 8 in the superpotential. So we had terms where the Higgs pair was multiplied by 1 singlet, 2 singlets, 3 singlets, 4 singlets, 5 singlets, and the singlets had vacuum expectation value in order to break some of the symmetries, and we couldn't give it mass to it. So then we said, okay, there must be a reason behind this, and we actually found the reason. It was an R-symmetry in this model. It was actually an R-symmetry which was affecting this pair of doublets, whereas we could, with the same mechanism, all the other pairs, sometimes we had 15 pairs, the other pairs we could make them heavy. So we had this discrete R-symmetry, and we could say this gives us a solution to the mu problem. Of course, mu is 0 at this point, and we could actually identify that these Higgs bosons, which we could not get a mass, were living in the untwisted sector. So here we had the clear signal that whenever we could solve the problem, we had the Higgs pair in the untwisted sector. And the fact that when you have an R-symmetry, of course the R-symmetry has to have some to distinguish between fermions and bosons, so typically it has a piece of the extra dimension Lorentz group in it. And of course, if the Higgs lives in the bulk, it feels this SO6 as an SO6 representation of the 10-dimensional Lorentz group, and that's the way it works. So it's a delocalized Higgs. The Higgs bosons live in the untwisted sector, and so that's where they are. Now, of course, the next is the question, what is actually the location of the top quark? Now, here I have to remind you that this was an input. The input was we wanted to have a large top quark Yukawa coupling, so we got it. But, of course, given the fact that we know that the Higgs lives in the untwisted sector, we now have to see how can we actually get a reasonable Yukawa coupling. And, in fact, of course, it would be good to have a maximum overlap with the Higgs multiplets. And, in fact, it turns out that in these models which we're considering, we found out that the top quark also lives in the untwisted sector. So both the top left and right, top bottom left and right, they live in the untwisted sector. And that's just the way you get this large top quark Yukawa coupling. Now the bottom, the right-handed bottom, and all these other fields of the third generation, they are not, they need not to be in the untwisted sector, and most of the time they are not. But the top is, so that happens. So this is something which we learned. So the top quark is in the untwisted sector, and the third family is distributed over various sectors. So it's not in a 16 of SO10. Now, in fact, in the Z62 orbifold, you cannot get 3 families which are full 16-dimensional representation of SO10. So that is actually, if it would have been possible, we would have tried to construct such a model, and the model would probably not have been good. So we would have gone one step back, because it would be difficult to work with a heavy top quark. Now the first and second family, in fact, there we want to have full SO10 representation, and in fact they can be found at this theta omega twisted sector where we have fixed points. And in fact this is where I get the zip code from. So this is the zip code for one family is A equal to 1, B equal to 1, and C equal to 1. And the one for the second family is that here, instead of 1, you have a 2. And in order to make the model, of course, you have to work out with the Wilson lines, break E8 down to SU3 cross SU2 cross U1, all the things. And in fact, what we will find here is that this model gives actually an explicit D4 family symmetry between these two families. These families have less overlap with the Higgs, so they are lighter than the top quark, and that would in some way explain their masses. Of course, the masses are more complicated to handle. There's a kind of Frogat-Nielsen mechanism which works here. So if you want to see how this all works, you have to work out the effect of the Wilson lines. I will not explain that to you, so you have to look at the paper and read out what this means. So unification, so let me just see unification. We have the Higgs doublets, they live in the bulk. The top quark also lives in the bulk, and the mu term is protected by an R symmetry. That means an R symmetry, of course, you know, is broken when the superpotential of the theory has a non-trivial vacuum expectation value. So if you have unbroken supersymmetry, this has to vanish. And the same reason also is the reason why the mu term vanished. So in that theory, we actually have also a Minkowski vacuum, because in unbroken supersymmetry, the mu term vanishes. The gravitino mass, of course, vanishes. And once supersymmetry is broken, you create a term for the superpotential, which gives you the gravitino mass, and then you will also get the mu term after you have broken that symmetries. The first two families are localized. They have smaller Yukawa couplings, and there will be discrete family symmetries. So now the next step we want to look at the hidden sector. And in fact, the models which we have here, they typically come with an SU4 gauge group as the subgroup of E8 in the hidden sector. And when you think of a hidden sector gaugino of condensate of SU4, and you fit the gauge coupling constant as you have it at unification, then you actually will predict that the gravitino mass is somewhere in the multi-TeV range. This actually brings me back to my first paper, which we had together, was in '85. So this was has a strange title, but it is gaugino condensation in the hidden sector of the E8 cross E8 theory. And the younger people of you might not know that in the old times everything was better. So when we were writing our papers, we had not just a general code to write formula, we had our personalized code. So font, yeah. So this is, I think this is your handwriting, yeah. So this was the Ibanez font. In fact, you see this was a later paper. So actually, you can see here the formula for the nose scale superpotential. At that time, actually, what we were looking at, we were looking essentially at the torus compactification, and we had an n equal to 4 supersymmetry, and in fact, that's also why this had this very special form, and this will also apply to these fields which are in the untwisted sector. So that's the right thing for the untwisted sector. For the twisted sector, you have complications. So in fact, if you want to see more, this is, of course, this is in the second paper we wrote, because in the first paper it turned out that it was my font. I had written all formally because you were not helping me. So this is yours. Yeah, I had to figure out where in some cases Jean-Pierre was also writing some formally. So the overall pattern which we'll get is actually something now. This is now cutting a long story short, that we're getting to a situation where we have a gravitino mass M3 which could be very large, but we have other masses which are protected. And among them are the gaugino masses. And they are protected by something which is 1/4 pi squared. It's the log of M Planck over M3 . A parameters are in that range, gaugino masses are in this range, and also the Higgses and the top quarks are in that range because they come from the untwisted sector. Whereas these particles in the twisted sector, they in fact are heavy. And so we have this kind of situation, as usually appears in this what is called mirage mediation, that we have such a situation. So looking at a closer look now, you have to see what does actually LHC tell us in order to test this scheme. So you can look at, so this was a benchmark model we did quite early for a gluino mass of 1 TeV. The green region up there was ruled out by the measurement of the Higgs mass, which at that time was 114 GeV. So the spectrum of this model looks that one has heavy scalars and then a certain spectrum of particles, and there is the Higgs here, which is 116, which was of course too low in this paper. But we had another model which was with a free TeV Cluino that had a gravitino mass of 15 TeV. So the benchmark model was here. You could see the stop is 500, so we put it here so that the stop was pretty light. Here you saw what the results of LHC at that time, and this was the measurement of the Higgs mass. The spectrum was looking like that. So this actually survived the discovery of the Higgs mass of 126 GeV, as you can see, because it had a Higgs mass of 126 GeV. But now you could see that the green region from the Higgs mass in the MSSM was really ruling out a lot of parameter in the space, as it is usually in the MSSM, whereas the direct measurement at that time were just here. So this is a model which in some way can evade some of the problems supersymmetry might have as the LHC, because it could have light stop particles, a compressed mirage spectrum of gauginos, which are not yet could not yet be checked at the LHC. So the message is large gravitino mass, gaugino mass is stop suppressed. Our fermion mass is of order M3 a mirage pattern for the gauginos and light stops, and this is a severe challenge for LHC. Now you can of course ask the question, can you say something about the absolute limit? And of course we do not know at that time. So I remember that in the old times they discussed a machine is called the SSC, the superconducting supercollider in the United States. And then at that time there was this discussion. This is the machine we built, the Hadron Collider, and this should clarify what happens at the weak scale. Whatever happens, it should clarify it. And these people, you see, they decided this machine should have 20 plus 20 TeV. This was quite amazing, because that's what, as at the time, when people still were believing that the top quark might be 15 GeV. Yeah, so this was. So then the question, so this no-lose criterion is maybe not really satisfied by the LHC, so we have to be happy. Now, one thing I had to tell, I was at SLAC at that time, and there was a bet book. So you could write a bet. So I bet this and this, and and there was this bet, I guess it was Okun who put the bet. I said, I bet that supersymmetry will be discovered before SSC gets into operation. And then Citrell didn't like supersymmetry, so he has immediately a counter bet. He said, I bet that supersymmetry will have been forgotten before SSC gets into operation. So now they are both right. So these are the conclusions, locations of quarks, leptons, and Higgs bosons. So this is the message. The Higgs and the top are in the bulk. At least the Higgs should be in the bulk. That's connected to the mu problem. Which in a certain way I forgot to mention. It was written that at least the directors, the former director and the director now, Casas and Munoz, they were actually suggesting this solution of the mu problems in the early 90s. And I didn't pay so much attention at that time, but apparently this was a good idea. So our fields, extra dimensions, and we have that situation. Now LHC, of course, is supposed to tell us all what will happen in the next time. And I was in Alsace in France. I made this picture. You see. So this is roughly what the LHC tells us. I haven't sin that yet. Yeah. So you can localize this if you know where D249 is. Yeah. Well, in any case, so this is where LHC leads us, and so does he know? So maybe. So it seems as if he knows. You see, he's pretty much concentrated. And the point is, of course, you see, you are crossing this age of 60 now. It's not enough to know. It's to remember. So, happy birthday.
Are there any questions?
Compared to the leptons,
We mean the lepton? No, the first two families live at this. One family lives at this 111, and the second family lives at the 211.
explain the differences in mixing angles?
Well, this is a question of going into detail in the model, having a Froggatt-Nielsen mechanism.
What I'm saying is if the third family strongly couples and the first two are only weakly coupled, you would expect small mixing angles in both the lepton sector and in the quark sector.
No, it's not necessarily true, because you have really to set up now a scheme where some fields get masses at order 4 in the Yukawa couplings, others at order 5, order 6. Now, these models have this flexibility. That's a question of model building. There's no reason. So you tell me what you want to have, and then we can discuss at what level which fields gets. It should certainly be that when you have these larger mixing angles, that these leptons in some way should have a different Froggatt-Nielsen mechanism there. But of course, we have not discussed that in detail, and we are not able to do that at this moment, given the fact that we do not know the full Kähler potential.
Yeah, Dieter?
In your four-dimensional gauge group, are there also generically leftover U1s which get then massive by four-dimensional or six-dimensional anomalies? So Z-prime gauge bosons, which perhaps could be even detectable at the collider.
Yeah, the point is that typically when we have this, when we are at the orbifold fixed point, I cut that short here. We of course have the same rank as before, so we have additional U1s. Typically what happens is that one of the U1s will be anomalous, and this will drive some vacuum expectation values because there will be a Fourier-Joblus term. We here assume that this Fourier-Joblus term drives it up to somewhere about n over 192 pi squared from the one loop form, and that therefore we get some waves that make this removes also the additional Higgses. This removes additional matter. So the construction was of the model making use, finding a vacuum in that theory where certain scalar fields have vacuum expectation value that remove all the stuff and only keep the MSSM. We did not try to keep one anomalous U1. If you would keep it, we would have a lot of stuff. So we would not have the U1, but I guess LHC will probably explode because there will be so many particles around that scale.
Yes.
Yeah, well, that's related to Ram's question. Do you have a way of making neutrinos so light, sort of seesaw?
Yeah, no, I guess there have been several papers on the fact how to get seesaw neutrino masses. That has been shown to work. And it actually has the nice property, even in the SO10 case. You see, typically you would say if you have an SO10, an underlying SO10 theory, you would have some 126-dimensional representation to give you the seesaw. But here we have these additional U1s, and in fact what we will see, we have some singlet fields which are having baryons, or maybe if I go back. We have some singlet fields which a lot of singlets. We have 51 singlets in that model. Some of them have lepton numbers. So I kept here hypercharge in B minus L. So you see this has lepton number 1. So these things in some way are singlets. So we have not 3 right-handed neutrinos. Very often we have some 15, 20, and they will appear in the seesaw mechanism, and it's possible to do that.
Okay, I see no more questions, so let's thank Hans-Peter again.